Alright, so in this video I'm going to be explaining another important article about domain adaptation. So this article in 2020 from Monash University. Graph convolutional networks have achieved impressive success in many graph-related analytic tasks. However, most graph convolutional networks only work in a single domain, incapable of transferring knowledge from to other domains or graphs. Due to the challenges in both graph representation learning and domain adaptation over graph structures. In this paper, we present a novel approach, unsupervised domain adaptive graph convolutional networks for domain adaptation learning for graphs. To enable effective graph representation learning, we first developed dual graph convolutional network component, which jointly exploits local and global consistency for feature aggregation. An attention mechanism is further used to produce a unified representation for each node in different graphs. To facilitate knowledge transfer between graphs, we propose a domain adaptive learning module to optimize three different loss functions, namely source classifier loss, domain classifier loss, and target classifier loss as a whole. Thus, our model can differentiate class labels in the source domain, samples from different domains, the class labels from the target domain, respectively. This is an example of unsupervised graph domain adaptation. Given a graph in a target domain where all nodes are unlabeled, domain adaptation aims to transfer knowledge from the graph of an existing domain where nodes are labeled to classify nodes in the target domain. So you see, for example, we have here three classes and we want to transfer for the target domain. This is the overall architecture of unsupervised domain adaptive convolutional networks. The input consists of graphs from source and target domains. So we have three components. It first uses a dual graph convolutional networks to capture local and global relationship of the graph. Then an intergraph-based attention mechanism is proposed to combine the output of different convolved data transformations. Finally, we introduce three classifiers working together to learn domain invariant and semantic representations effectively for training the source classifier, domain classifier, and target classifier respectively. So there are some shared parameters between the source path and the target path. And after we've gotten that use attention mechanism, we have three different losses. We know that we use source classifier, we use cross entropy for source classifier, as well as target classifier. But for target, because we don't have label, we just use entropy loss. For the domain classifier, we use the adversarial technique. You could use maximum mean, but here in this paper, they use adversarial approach. So it's a game. We try to learn these backbones such that we fool this discriminator here. So we have three components: node representation, intergraph attention, domain adaptive learning. So they use this local consistency network. So the output of the ice hidden layer is just this sigmoid of this diagonal matrix times adjacency times diagonal times z times w. But here, this is just local consistency that everybody knows. But they use global consistency as well. And for that, they use this frequency matrix F. Now we have pointwise mutual information after calculating the frequency matrix F. Once you get F, the ith row of the F is the row vector F sub I. So the value of F sub I j here is the number of times that xi occurs in context C sub j. So now we can calculate this pointwise mutual information. Since our node embedding module consists of two networks, which is based on similarity of adjacency matrix A, another network is derived from similarity. And then we have this intergraph attention. After performing node embedding module for source and target, we obtain 4 embeddings for source and target graph. We need to aggregate embeddings from different graphs to produce a unified representation. For each domain, as embedding from local and global consistency network contribute differently to learning representation. We propose an intergraph attention scheme to capture the significance of each embedding. So we use the original inputs as the key of the attention mechanism. We then perform attention on each domain outputs. 2 attention coefficients are computed. So K here denotes an output is from the source domain S or the target domain domain T. And J here is just the shared weight matrix to make the input have the same dimension with the output Z. Then we normalize the weights with this softmax layer. Then we get the final output Z sub S, C sub S, and Z sub T. As I said, we have just 3 losses for a target and source, and for our domain adaptation that we use adversarial technique. This adversarial technique that we use. For target, as I said, because we don't have labels, we just use entropy. This is the only thing that we can do. So once you have given your source domain, target domains, the number of layers, you want to output the embeddings and the source classifier, domain classifier, and target classifier. So we backpropagate and we learn these source classifier, domain classifier, and target classifier. So when we go from any domain to any target, we have a different accuracy. So for this paper, they have this accuracy for domain going from source domain D to target domain C.